day to all of you, and today we'll continue our discussion on stability of incrementally raised embankments. This is what we started last time, and we will carry it through to see how we make these embankments stable, what are the critical factors which affect stability, and what are the design issues that we should be looking at very carefully while raising these embankments incrementally. So last time, if you would recall, we had said that a pond may be filled up in 20 years, and we would like to raise it incrementally. If I use the traditional method, suppose I was to raise it once every 5 years, then it would come to the top in 20 years. So this would fill up in 5 years, then this would fill up, then this would fill up, and then this would fill up. This is the conventional way of making a dam. So making an embankment incrementally by the conventional method is not very suitable, because in the beginning you have to make a very wide base, and then as you go upwards, you have the width decreases as you go upwards. But a lot of investment in earthwork takes place in stage 1. So conventionally what we do is we either use upstream method, where the earthwork is smaller, as you can see, or the downstream method, where the starting earthwork is small, and as the dam progresses, more and more earth is added as you go upwards. And the centerline method is in between the two. The difference in stability is that typically the failure surface in the upstream method passes through the loosely deposited slurry material, and the factor of safety of this slope is usually low during earthquakes. In the downstream method, the critical failure surface passes through the compacted material. So the stability of the embankment is better. In the centerline method, it's a hybrid of the two. One thing which I talked about, in the upstream method, as we can see, the internal drains are provided in each dike, and consequently the phreatic line which develops is close to the downstream slope. In contrast, in the downstream method of construction, the drains are far away from the downstream slope. This is the final drain. Consequently, your phreatic line looks like this. Bulk of the embankment is not saturated. So we looked at the fact that the factor of safety could be evaluated using the infinite slope failure methodology for the dry case and for the flow parallel to the slope case. And we said that the factor of safety when C dash is 0 becomes tan phi dash by tan beta, and if there is flow parallel to the slope, it becomes gamma b by gamma t tan phi dash by tan beta. If I look at the phreatic line, in the case of dry soil, there is no phreatic line. So the factor of safety is governed by tan phi dash by tan beta. If there is upstream reservoir is full, and for some reason there is no internal drain, then the phreatic line will come and join the downstream slope. So flow here is parallel to the outer slope. So the factor of safety in this case becomes gamma b by t, gamma b by gamma t tan phi dash tan beta by tan beta. So this has a high factor of safety, and this has a low factor of safety. If I look at the upstream method of construction, my phreatic line looks something like this. Here the flow is close to the surface. In the downstream method of construction, the phreatic line looks like this. It is far away. So the factor of safety for the downstream method of construction is very similar to the factor of safety for the dry slope, because this is primarily dry and your failure surface will probably go like that. Okay. Whereas in the upstream method, the failure surface goes a little deeper, and therefore the factor of safety lies between these two values. This is high, this is low, and upstream method lies somewhere in between. So I'm going to take an example and show you how various parameters affect the stability of embankments constructed by the upstream method. A 20-meter high embankment has been constructed. The outer slope has been kept 3 horizontal to 1 vertical, and we have varied the phreatic line, we have varied the horizontal seismic coefficient, and we have varied the compaction as well as the internal drainage. So that's the problem that has been analyzed. Please note that this is first starter dike is 8 meters high, and there are 1, 2, 3, 4 raisings of 3 meters. The downstream slope is 3:1, and there is no offset at the level of the crest. Normally you may have this kind of a construction, or many times you will move the upstream dike a little behind and leave a 2 to 3 meter wide pathway, so that that can become an inspection pathway. We used this analysis for an ash pond. So the properties of the ash for loose uncompacted ash, this is hydraulically deposited, and compacted ash, which is compacted by rollers, were taken. The important thing to note is that the phi dash for the hydraulically deposited ash was taken as 28, and for the compacted ash was taken as 35. And stability analysis were done using circular slip surface methods, using a grid of centers, and the minimum factor of safety was identified for the critical failure surface. So here is the first set of variables. What is stated is you could have a high phreatic line, a medium level phreatic line, and a low phreatic line. When will the phreatic line be low? When the pond is of low height, ash has just filled up a meter or two, and the water is 1 or 2 meters in the pond. As the dikes rise, and as the ash rises, water levels will go up. So here what it shows is that towards the end of the life, your water level may be very close to the top, and then you may develop a high phreatic line. So intuitively what we can say is, for low phreatic line you'll have a higher factor of safety, and for high phreatic line you'll have a lower factor of safety. And also we have said that let there be no seismicity to 0.15 alpha h, so this gives you the kind of seismicity. So how does the factor of safety change? If the embankment is on uncompacted loose pond ash, alpha is 0, there is no internal drainage. When the phreatic line is low, we get a factor of safety of 1.6. But when the phreatic line is high, we get a factor of safety of 0.71. So when the phreatic line is here, the factor of safety of this slope is 0.71. When it is here, it is 1.6. So if you recall, the acceptable factor of safety is 1.5. So this looks good. So this embankment, or these incrementally raised embankments, will remain stable as long as the phreatic line is low. But the moment the phreatic line becomes high, the factor of safety will fall below 1, and you will have a failure. If I now add on to it seismicity, now do remember that the acceptable factor of safety for a static case is 1.5, and the acceptable factor of safety under earthquakes is 1.05 or above. So I remember that for low phreatic line, no earthquake, I had 1.6. And as I increase my alpha values, the factor of safety falls. At 0.15 G, which is pretty high, you get a factor of safety of 1.05. The slope still remains stable, because 1.05 is the acceptable factor of safety for a small duration event. However, in the medium phreatic line case, where the factor of safety was above 1.1, during earthquake it falls to 0.7, indicating again that if you have a medium level of the phreatic line and an earthquake comes which is above 0.05 G in the horizontal acceleration, your embankment is likely to fail. Does compaction make any difference? Well, let's up the phi value from 28 to 35. Let's say we are able to compact the entire ash by some means. Then what happens? When the phreatic line is low, I had 1.6 if you recall. If I compact the ash, the factor of safety goes to 1.9. As long as it is low, 1.6 falls to 1.19 under an earthquake. But do remember, on uncompacted loose ash, when the phreatic line is high, anyways this embankment was failing. Can compaction prevent this failure? That's the question we would like to address. 1.6 went to 1.9 when the ash was compacted. That is very good. But 0.71 went only up to 0.82. So compaction cannot offset the problem of a high phreatic line if there are no internal drains, because the phreatic line starts meeting the downstream slope and your factor of safety tends to become gamma b by gamma t tan phi dash by tan beta. Now what we do is we install internal drains. There are two options. I can install an internal drain like this, a chimney drain at the midpoint of the base, and another option is that I can take the drain even back deeper. The idea is that when the internal drain is in the form of a chimney drain, then your phreatic line will be joining the top of the chimneys, whereas here it will be back. So the phreatic line will become a little more further away from the downstream slope. However, there is a danger. If you take this very deep and there is water here, the seepage levels will be higher. You will get more water out of the pond because it is very close to the upstream slope. So what do these drains do? Let's have a look. We remembered that when we had compacted dense pond ash, we had gone up from 0.71 to 0.82, right? Now I put a chimney drain, I get 1.14. That's a substantive increase. And if I put a deep horizontal drain, high phreatic line, I get 1.70. So the drain is the most critical requirement. If you can put a good drainage system, you will get a stable embankment. So observations. The stability of the dikes is significantly affected by the location of the phreatic line as well as the magnitude of the seismic coefficient. And we were looking at a slope of 3:1. And 3:1, if there is no drain, you can have failure. 3:1, you have deep drains, you may not have failure because the phreatic line is kept well away from the surface. So proper compaction helps increase the factor of safety, but internal drainage is the most critical factor for slope stability. Okay, so that's the message that I'm trying to get you. Keep the phreatic line well away from the downstream surface. So if you look at the ash ponds designed by NTPC, National Thermal Power Corporation, you'll find the designs like this. Typically this is 3:1 slope, but they keep their embankments away from the crest. So though this is 3:1 and this is 3:1, the total slope is about 3.5:1, the average slope, because every time the embankment is kept away, it is not continuously going up. Secondly, they keep the chimney drain and a blanket drain and a rock toe. So in this manner, they are able to keep the phreatic line away from the downstream phase. And they are collecting the water of each stage in a toe drain and taking it away, right? So we are not allowing the water of this drain to come here, but if it overflows, it will come here. This water is collected in this drain, and in the lateral direction, the water is taken out by overflow. So that is the design which is used for upstream raising. Do remember that in any case, this ash has not been compacted. So you still have sometimes issues about this being very well made, but the failure surface going through soft ash or loose ash and giving you failure. Critical to all this is the location of the decantation well, and let me try and highlight this problem. This is the slurry pond. Let us say this is the area that has been given to us for the purpose of design of a slurry pond. And we are going to do upstream method of construction. So I need to have two ponds. So what I'll do is I will bifurcate this into two so that one pond can be working, another pond can be closed. So I do the partition, I do a partition dike, now I have two ponds. One can be working at one time, the other can be closed, the other can be working at one time, the first one can be closed. And I tend to keep the decantation wells close to the embankment. Why? So that I can reach them for maintenance. You recall I have shown you location of the decantation well is typically close to the embankment. If you are close, you can put a little connector from here to here and you can maintain it. You have to go and close the openings, the ports from time to time as the water level rises. So you have the decantation wells here. In such a situation, where will you put your slurry inflow points? We have talked about Garland Canal. So I'll put my slurry inflow points here, far away from the decantation well, so that if I put an inflow point here, the slurry has to travel this much distance and the fines will settle down. If I put it very close, it will be an issue. So this is the way by which you do a Garland slurry arrangement. Your slurry pipeline comes here, and let us look at this pond. You will be sending in the slurry from time to time through these inflow points. This distance will still have to be the minimum distance required for the purpose of settling of the fines. Now, when I allow inflow like this, where will the coarse particles settle and where will the fine particles settle? The coarse particles settle close to the inflow point. This will have a decantation pond, in the sense the water will, so the fine particles will tend to settle here. So if I look at this, I'll have coarse ash and tailings very close to all this area, okay? But I'll have fine ash and tailings here. So what happens? I have to raise this now by the upstream method. The upstream method means my new dike will come on the inside of the pond, right? Here, here, and here. So I can stop one of the ponds and allow this to dry up, and I can make my pond like that. The only problem is that on this end I am having fine tailings. So the strength is low. They don't dry out that easily because they hold more water, and many places you will find that the increase of height of the pond is like this. You are able to increase the height here by moving the dike inwards after 3 years, and again after 3 years, and again after 3 years. On this side, you have increased it after 3 years, but now you find that your decant well is getting buried. You see, if you start moving inwards, then you should have kept your decant well away, taking into account the fact that you will have 5 raisings. If I wanted 5 raisings, maybe the well should have come here. So normally, this is a problem which is encountered in many of the old slurry ponds, that the decantation well has been kept very close to one of the main embankments. And this creates a problem. How would you tackle this problem? I would like to keep the well here. If I keep the well here, the only problem is how to reach it, right? I'll have to reach it to maintain it. So anyways, what currently is done, as you will see, is that after 1 raising or 2 raisings, when you come very close to the decantation well, you move the well on the upstream side. So first dike is here. After 4 or 5 years, if it fills up, the second dike is here. After 4 or 5 years, if this is getting buried, you put a cross connector and make another well here, and then you do the raising. Still you are doing the raising on fine ash, which is not something which you can't do, because you can make the slope very flat, but not desirable. You should have coarse ash or coarse tailings on which you should put your embankments. So is there another way of doing this, which we are not adopting yet? Well, one would like to propose the following. Let us say we have the same slurry pond, okay, and I make the partition. Now another way of doing this is to put the decantation wells here. Please see the location of the decantation well. Now what is the, how are you going to reach it? We anyways have a partition embankment, right? And what is a partition embankment? It is not a permanent embankment. Please note that the outer embankments are the permanent embankments which are going to be there for the whole life of the pond and even afterwards. If I was to try and capture this, this is my starter dike. Let us say I am going to have 3 raisings. So I have my 3 raisings, and this is the final. These external slopes are going to be there always. What is a partition dike? Partition dike is that you make a dike here in the center, right? You make a dike, so you can use this one at a time and this another at a time. Now you want to go higher, what will you do? When this pond fills up, how will you make your next dike? You can make it by the center line method, right? You can make it by the center line method, and like this you can go up. Now what is different between the other dikes and this dike? These dikes are not permanent dikes. Why? They'll become buried with time. Suppose this is your end of your 20 years of operation of the ash pond, the dikes are buried, right? So even if one dike fails, slurry goes from one pond to the other. Whereas these dikes cannot fail because there will be village or humans or road or something nearby. So you can't send your failed slurry into habitation or into infrastructure facility. So partition dikes are temporary. So what happens is I make my well close to the partition dike, and that's what I've shown here. You can always drive on this, and you can drive on this, and then you can have a connector. So now what happens? How does the raising take place? Now when I have the decantation wells more toward the center, what is happening? Your garland pipeline arrangement can be like this, right? Now when you can have like this, then the coarse ash will fall here, coarse ash will fall here. So this is an alternative way of doing things. Yes, the decant pipes will be longer. You are going to have a decantation pipe coming through, this will be longer, no doubt about it. However, this is reachable from here and this is reachable from here. Then how does it play out? The coarse ash settles here all along, and the decant pond zone, the water comes here. The fines are here. So the fines are in this portion. Agreed? Now if I want to do my incremental raising, I can actually raise it like this because this is coarse ash all along. The partition dike will go up by the centerline method, so it will not bury the two decant wells with time. The partition dike is sitting on fine tailings or fine ash. Okay, its stability is a little less. However, the partition dike is only going to be visible for 3 to 4 years, then it becomes buried. So it is not going to be something which is going to have a catastrophic effect in terms of failure. So then what you find is that the raisings go like this. Now you are able to raise everything on the inward side in a symmetrical manner. And your ash pond or a tailings pond which was like this keeps on coming closer, and say you have reached your height of 15-20 meters, you can close it at the top. Even you can go higher and close it, but you are putting your embankments on coarse material, and that's the way it looks. There's one more aspect of stability which I'd like to talk about. Now, phreatic line is very important, and remember in all that we showed you here, where is the water now? The water is far away from these embankments. Can I just go back to the earlier thing? Where is the water here? The water is here, right? As far as the stability on this side is concerned, it's not a problem because the water level is far away. But what about these embankments? The water is impounding on them. That means the phreatic line on this side is always going to be high. It's always going to be high. Whereas now in the new arrangement, the water level is far away. Of course, it is still possible that you have excess water and you are filling this up like a lake. That is possible, but bulk of the time the water could be far away. Therefore, the phreatic line as far as the outer embankments are concerned would be low, and therefore the stability of the outer embankments will be better. So all the new arrangement also allows you better control over the phreatic line. But one more thing is happening, and that is the requirement of liners. Over the past 2-3 years, more and more regulations are coming in that you must have liners at the base of all slurry ponds. And this is having an effect because the moment you put a liner, the water can't go down. and therefore it tends to remain inside the pond, and that has an effect on the phreatic line. And let's have a look. So let us say this is my slurry pond, this is the peripheral embankment. Earlier it was unlined, right? And what used to happen? You would have your ash and slurry water up to this point, and then I had to make the next raising, so I would stop one portion of my pond from working and do my discharge in the other portion. As I did my discharge over the other portion, I used to allow this to dry out for 6 months. That's been a standard operating practice. What will happen in 6 months? The slurry water will tend to go down. Partly it goes through the dike to the chimney drain. Bulk of it used to go down because it could seep into the ground, and some of it would go towards the well. But remember, the well, the lower ports are now closed. So if the lower ports were open and there was a filter pack around it, then the water could have been drained out through the well. But at the moment, the design is that the lower ports are sealed up as you go higher. Still, after 6 months when you came, what we would normally observe is that the slurry water level inside the ash would have gone down, and this ash would be either moist or dry, or this tailings would either be moist or dry. When this becomes moist or dry, your earth moving equipment light earth moving equipment can move over this. So it is possible for you to make the embankment. If this is high, then even you can't stand, and even earth moving equipment can't stand if the water level is near the surface. So this is the standard method for raising this by the upstream method. Now what has happened? The government or the regulatory authorities are saying, please line the ponds. Conceptually, let's line it. Let's make a dike and let's line the pond. So how is this good or bad? Well, you now put your slurry water, and in 4 or 5 years your first raising is full. Then you say, okay, now 6 months we will allow this, and let's move to the next one. You start filling the next one and you allow this to 6 months. Where does the water go? Can it go from through the chimney drain in the dike? No, because if you have got an impervious liner here, it's not going to allow the water to drain out. Can it go into the ground? No, because you have a liner at the bottom, an impervious liner, maybe a compacted clay plus geomembrane. Can it drain out through the well? Perhaps, if your ports are not properly closed. If your ports are closed, then the ash is at the top. Only overflow water can go in, not from the bottom. So what you have done is created a bathtub. You created a bathtub and you have plugged the drainage. Now after 6 months you come and the water is just moved down by 1 meter. And you start to construct on it and you have all kinds of problems, because though the water has moved down, there is some capillary fringe and it doesn't support. So you wait a little longer and maybe you'll do it after a year. But the drainage becomes very, very slow. And constructing on this soft saturated deposit is a big problem. And this is being reported from the field from time to time. Not only that, see what happens later. When you fill this pond, now you have made the dike and there's a chimney drain. This is the first raising. Can you say this? This is the starter dike. This is the first raising. In the first raising, you have a chimney drain. Now you start filling the slurry again. First, this slurry water used to go down. It used to go down through this. It used to go back. Now what is happening? It can't go down. It can't go through this. In some cases, it has been reported it starts to ooze out from here, from this side. So in 1 or 2 cases, there have been reports of seepage through the toe of the first raising. This dike is not having any seepage. Why? Because the liner is functional. But this dike doesn't have a liner. So water can come out to this. So this starts to create stability problems. So the only way to put a liner in a slurry pond is also to have bottom drainage. You remember your leachate collection layer for landfills. The idea was not to put a liner and have no bottom drainage. Then you would have a bathtub effect, and even that would drip. As I used to tell you, that if there is ponding of water on this rooftop, Unless it is drained out, it will drip through even if it is impervious or very low permeability material. The same story here. For you to do the next raising, you have to drain out the water, which means two things. You must have a bottom drain, you must have a drain through this dike, and you must also be allowing in the decantation well the water to come out. And if I was to now look at this liner, it has not been stated in most of the regulatory environment that there should be a bottom drain. But what are we saying is, if you have a geomembrane at the bottom, then please put a sand layer of 30 centimeters, just like your leachate collection layer if you recall, and a geotextile filter or a natural filter on top, so that from the ash and the tailings the water will come here, and then give it a slope. Give it a slope towards the decanting side. Okay. If I want to drain it through this, what should I do? If I want to drain out the water through the dike, what should I do? So let us say this is my dike, and it has a liner. Okay. Now I want to drain out the water. I still want the liner to remain in position. Then I need to have something which will go through this liner and come out on the downstream side, right? A simple example is, let me put a pipe. If I put a pipe, then I can have a toe drain here and the water can be collected, and I can have a rock toe here. But the problem with pipes is, with time, if there is differential settlement, then the pipe can crack. So one of the ways of doing this is, make a drain, a trapezoidal drain, or you can make a trench drain, whatever you want. But the idea is that from here you should be able to carry out clear water. What does a trapezoidal drain look like? So this will be your drain, cobbles and boulders at the center, then gravel, and then sand. So it's a flexible drain. It's not like a rigid pipe or a jointed pipe where you can have a problem. Here you have a flexible drain. Such a drain, this is a cross section here. Such a drain would allow your water to pass through it, and even if it settles a little bit, it's not going to crack. So these are all filters around it, such that the fine ash or the fine tailings don't come through it. And remember, you will need a rock toe here and a filter here and a toe there. You have a sand layer at the bottom, I've already told you that will have to be interconnected to this drain, so that within the embankment, if I'm now looking at this embankment from the top, that's the crest, that's the downstream toe. At certain locations, these drains are coming through to allow the water to drain out. All that we are saying is, if you are putting a liner, it should be a bottom drained liner. That means any liquid which is resting on top either goes to the well, in which the bottommost ports still allow water to come through, because by putting a gravel pack around them, and you may still allow passage of the drain, the water to drain out through the embankment as well by properly designing it. And this is, if you want to make the drain below the ground, then you can make a trench drain. How does a trench drain look like? Exactly the opposite of what it looks like here. So this is below the ground and this is above the ground. So if this is your ground, either you can have a trapezoidal drain or you can make a trench and have a drain, either of the two. But you would be collecting the fluid there, and this would then be lined, because you would have to line this so that whatever the water is going out, you're not supposed to let it go into the ground. Consequently, if you look at the options, so here you see that here what they have done is they have taken the liner overlain by a blanket drain through the dike, and they have therefore allowed the water to collect at the drain. In such a case, the ponded water would come down and you would be able to make your first raising with no problems. So, control of phreatic line continues to remain the single most important aspect affecting stability of slurry ponds. Most of the failures, and in the next lecture we will be discussing what kind of failures occur and how do you remediate, how do you take remedial action against those failures. Most of the failures occur because the phreatic line has not been controlled or the filters have not been made properly, and therefore the fines wash out and the piping take place. Design and construction of filters, drains, rock toe and berms should be done carefully at all critical locations. Any person who cuts the corners as a designer on the design of the filters has always faced problem of the failure of the upstream method of construction. And why so? Because once, please understand that both ash and tailings are in the sand, silt, sand range. They have no cohesion. They are highly erodible. So once the water gets a pathway of coming out, it starts to come out, and if the fines can also come out, then the fines will gradually start to come out and cause piping. And once piping takes place, then the rate of flow keeps on accentuating and there is collapse. If water can come out and no fines can come out, that's a great control measure. For that, you have to design these transition filters so that no fine material can come out of the pond. So with this we will end here. If there are any questions, I'll be happy to answer, or any clarifications that you would like on this topic. But do remember that despite doing everything, we are still putting the upstream embankment on a loosely deposited hydraulic fill. And after the operations are over, let us say a thermal power plant has been designed for 35-40 years, or a mine is going to work for 50 years. After everything is over, no water will come in. At the moment, slurry water. As long as it is in operation, a lot of slurry water comes in. And as long as slurry water comes in, there is this problem of stability, because you can always have either a piping failure or earthquake induced failure, because it's a soft material, and in slope stability analysis you will find out that you can always have liquefaction in the silty sand, sandy silt, which has not been compacted. So be careful, keep the phreatic line under control, keep it low or keep it well drained, and no fines should come out. Okay? So thank you, have a good day.